Hello and welcome to what I'm going to call topic 3.61, the derivative of inverse trig functions. You may ask, why have I broken down chapter 3.6 into these two parts? And it's just because I think it's important for everyone to see the proofs so they know how the functions work. Because if they don't know the proofs and they don't know how the functions work, even though they can still apply them, it is better for you to know why you're doing it, or what is the reason behind the power rule and all that stuff. So in today's video, we're going to be going over the derivative of these inverse trigs, which we're going to use the same method that we used in the last video for logarithms. This time we just have to do it 6 times. Also have to use a lot of trig for this, so hopefully y'all have done math 1405 or whatever your either college or high school trig classes. Alright, so let's get started. So for this derivative of sine inverse of x, we start out with what we know. We know that sine of sine inverse of x is just equal to x. Okay. What does that tell us? Well, now we can take the derivative of this, and we would get the derivative of sine inverse. That's going to be cosine of sine inverse, as that's going to be the derivative of the outside times by the derivative of the inside, but we don't know what the derivative of the inside is yet, so we're just going to call it dx of sine inverse of x. However, we know what this is, so in theory we can solve for this. So we're going to say d over dx, or the derivative with respect to x of sine inverse of x, is equal to 1 over cosine of sine inverse of x. Now, believe it or not, we can actually make this simpler. So what we're going to do is we're going to bring out a good old friend of ours, the unit triangle. And what is this really asking? What is this sine inverse of x? Oh, this is the angle such that sine is equal to x. So this sine inverse of x, well, we know that if sine is equal to x in this case, and sine is opposite over hypotenuse, this hypotenuse must be 1, and this opposite must be x. Now, what is this cosine? We can find this cosine, actually. So, we can use our Pythagorean theorem and say 1 squared minus x squared is equal to this side length, a squared. Take the square root of both sides. So, we're left with the square root of 1 minus x squared is equal to a. Cosine is adjacent over hypotenuse, so plugging all of this in, we get the derivative of sine inverse of x is equal to 1 over the square root of 1 minus x squared. And that's the derivative of sine inverse. Now let's do cosine inverse. So we once again say that we're going to start out with what we know, which is cosine of cosine inverse of x is equal to x. Okay. Now we're going to take the derivative of both sides with respect to x. The derivative of cosine is negative sine of the inside function, which is still cosine inverse of x, times by the derivative of the inside function, which we do not know. So what we're left with is a function where we can solve for this derivative. So let's solve for this derivative. So we get d over dx of cosine inverse of x is equal to negative 1. We're just bringing this negative 1 up top of sine of cosine inverse of x, or arc cosine, if you remember that notation. Well, once again, we bring out our triangle. Oh, I should probably use a different color for this. So, what's cosine? What is the cosine let's say this is cosine of theta. If cosine of theta is equal to x, Well, then that means that it must have an adjacent of x and a hypotenuse of 1. So now all we need to do is solve for this missing side length. Let's call it b. So we have 1 squared minus x squared is equal to b squared. And what this really means is the square root of 1 minus x squared is equal to b. Well, if we're looking at the sine of this angle, that's going to be b over the sine. So the derivative of cosine of inverse of x is equal to negative 1 over the square root of 1 minus x squared. Boom! Isn't that amazing? What this is really, really interesting about this, a derivative of a transcendental function here becomes an algebraic function. And I find that fascinating. But I digress. So now I have 2 practice problems for us. So I want to find the following derivatives. So we want to find the derivative of sine inverse of 3x. Well, that's actually really easy for us, isn't it? So we know that the derivative of sine inverse of x is 1 over the square root of 1 minus x squared. We have to remember that this argument here is going to be, in theory, our x squared that we're thinking of, though. So what this is going to look like is we are going to get 1 over the square root of 1 minus 3x squared times by the derivative with respect to x of 3x. All right, what is the derivative of with respect to x of 3x? That would be 3 over the square root of 1 minus 9x squared, and that doesn't get any simpler. All right, for this next one, we have once again a general derivative. So we're going to take the derivative of cosine inverse of the natural logarithm of x with respect to the natural log of x times by the derivative of the natural log of x with respect to x. So the derivative of cosine with respect to the natural log of x is going to be negative 1 over the square root of 1 minus the natural logarithm squared of x times by the derivative of the natural logarithm with respect to x. That's 1 over x. So we can now combine these. So we get a negative 1 over x square root of 1 minus the natural log squared of x. And that's our answer. All right. Let's get on with the more derivatives. So now we have to do the derivative of tangent and the derivative of cotangent. So, once again, we start out with we know. We know that the tangent of tan inverse of x is equal to x. Take the derivative of that with respect to x. The derivative of tangent is, come on, remember it. Remember it. You know it's right there. Oh, yes, it is secant squared of tangent inverse of x times by the derivative with respect to x of tangent inverse of x is equal to 1. Now what do we do? Oh, this is where it gets challenging, a bit more interesting even. So we have to divide this over, so we get d over dx of tangent inverse, or let's call this arctangent because this is about to get messy if I don't. Tangent of x is equal to 1 over secant squared of tangent x. Tangent inverse of x. Now what do we do? Well, my friends, we just use another triangle. Isn't that amazing? More triangles. Well, tangent, if tangent is equal to x, then that means that our opposite must be equal to x, and our adjacent must be equal to 1. And if that's the case, then our hypotenuse must be equal to the square root of 1 plus x squared. Well, we're taking the secant of that. So we're taking secant, so the derivative with respect to x of arctangent of x. Well, secant is the adjacent, the hypotenuse over the adjacent. So what we're going to see is we are going to get 1 over the square root of 1 plus x squared squared. So for our final answer, we get the derivative with respect to x of arctangent of x is equal to 1 over 1 plus x squared. Very similar, but still holds true where there's no longer a transcendental function in there. Now let's do the same thing for cotangent. Well, cotangent, apparently I forgot the inverse up there, but cotangent of cotangent inverse of x is equal to x. Okay, now what? We take the derivative with respect to x. Okay, what do we do now? Well, the derivative with respect to x of cotangent, that's negative cosecant squared of cotangent inverse, which for all intensive purposes I'm going to call arccotangent. A lot of c's of x times by the derivative with respect to x of arccotangent of x is equal to 1. So if that's the case, then the derivative with respect to x of arccotangent of x must be equal to negative 1 divided by cosecant squared of arccotangent x. All right, now what do we do? Once again, we bring it to a triangle. At this point, I'm getting pretty certain that this triangle is pretty cool. Let's see. So we draw in our triangle. What's cotangent? Well, it's going to be adjacent over opposite, meaning that our adjacent side must be x and our opposite side must be 1. Well, if that's true, then once again, our hypotenuse must have a length of the square root of 1 minus x squared. And since we're dealing with cosecant, it's going to be the hypotenuse over the adjacent, square it, so we get d over dx of arccotangent of x is equal to negative 1 over the square root of 1 plus x squared squared. So for our final answer, we get the derivative of arccotangent of x is equal to negative 1 over 1 plus x squared. Do you see a pattern with these? The cofunctions are just the negative of the complementary functions are just the negative of the normal trig functions. And that still holds true. All right. Well, let's do our final two. Or actually, no, we have some practice problems first. The derivative, so we want to have the, this is going to be a mess. A messy mess. So, we are taking the derivative of cotangent inverse of sine inverse of x. So, what is this going to look like? Well, to start out, we take the derivative of the outside function. So we have the derivative of cotangent inverse of sine inverse of x with respect to sine inverse of x. Then we multiply that by the derivative of sine inverse of x divided by the derivative of x, or divide that by the not divide, but take with respect to x. So this is just the chain rule. And anytime that I'm writing this out, this is just to really highlight how the chain rule works. So we're taking the derivative of cotangent, so this is going to be 1 over 1, or sorry, negative 1 over 1 plus the derivative of cotangent is negative 1 over 1 plus x squared, which is going to make this sine inverse of x squared, times by the derivative of sine inverse of x with respect to x, which is just 1 over the square root of 1 plus x squared. Does this simplify? Probably not. So I'm going to leave this almost as is, but we're going to combine these fractions and just say that 1 plus sine inverse of x squared times by the square root of 1 plus x squared. And that's our answer. Good luck finding the derivative of that, or sorry, the integral of that, whatever that means. Alright, continuing on for this arc cotangent. Once again, a chain rule derivative, but this one isn't really that bad. So, the derivative of arc cotangent. Oh, I did both arc cotangents for this, and that's fine. So we are going to take the derivative of arc cotangent, d over dt of, I don't think this is proper notation, but I'm going to call it proper notation, of arc cotangent of t squared times by the derivative with respect to t of t over 2. So what does this give us? Well, the derivative with respect to t over 2 of arc cotangent is going to be negative 1 over 1 plus t over 2 squared times that by the derivative of t over 2, which is just 1/2. All right. I suppose we can expand this out, so we're going to get negative 1 over 2 plus t squared over 2. Now what do we want to do? Well, I'm going to do something, and I'm going to multiply both the bottom and the top by 2. And the reason for this is because my math teacher loves to get mad at me if I leave fractions and fractions. So we are going to get 4 plus t squared, or sorry, negative 2 over 4 plus t squared as our answer. All right. Finally, we have our last two inverse trig functions. So let's find the derivatives. So secant, once again, secant of secant inverse, or of arcsecant, secant of x is equal to x. Now what? We take the derivative of both sides, and this one's going to be a bit more of a mess than all the rest. So the derivative of this, well, we get secant of arcsecant of x times by tangent of arcsecant of x times by the derivative with respect to x of secant inverse, which I'm just going to have to change the notation on you to save space, is equal to 1. All right. Now what do? We divide everything to the other side. So we get d over dx of secant inverse of x is equal to 1 over secant of secant inverse of x times by tangent of tangent inverse, or sorry, tangent of secant, tangent of secant inverse of x. Well, what do we know here? We know that the derivative with respect to x of secant inverse of x, well, we know that this, so we know that 1 over, well, secant of secant inverse of x, for some reasons that I'm not going to go into, we're going to call this the absolute value of x. But for the main reason, it's because we always want this to be positive. And that's the way that it's going to work out with our definition of secant. And then we have the square root of, or actually, no, I should not be doing the square root just yet. So what's tangent of secant inverse? So in order for us to find that, we once again go to our trusty triangle that we've learned so much about today. Well, secant is really the hypotenuse over the adjacent. So that's going to be x over 1. So we're going to get x squared minus 1 for our side length b. Tangent is opposite over adjacent, so we just get times by the square root of x squared minus 1. And that's our derivative. So the reason why secant has this absolute value of x inside of it is because it's always increasing. And because of that, we can't have a negative x value in here on its graph. So we say that the derivative of secant inverse of x is 1 over the absolute value of x times by the square root of x squared minus 1. So that's the reason why we have this absolute value in here. And another definition of secant, there is no absolute value. However, for the one that I use, there is. For this next one, we need to find the derivative of cosecant, which is going to look very similar. I'm going to have to, erase some of this stuff. Or at least resize it, probably. Yeah, I can resize it, make it a bit smaller. There we go. Give me a bit more space. So, where do we start? Well, we know that cosecant of cosecant inverse of x is equal to x. Take the derivative of that with respect to x. Well, the derivative of cosecant is negative cosecant of cosecant inverse of x, which, as of right now, we're just going to simplify this immediately to the absolute value of x. Well, you know what? I'll write it out first. Cosecant of cosecant inverse of x times by tangent of cosecant inverse of x. Cotangent, not tangent. Cotangent times by d over dx of cosecant inverse of x is equal to 1. Okay, now what? Well, this over here is just the negative absolute value of x. We're going to then call this cotangent of cosecant inverse of x times by d over dx of cosecant inverse of x is equal to 1. Divide this over, so we get d over dx of cosecant inverse of x is equal to 1 over cotangent, or negative 1, absolute value times by cotangent of cosecant inverse of x. Alright. Now what do we do? Okay, so now we once again go to our triangle. Very repetitive. Our triangle, well, we're looking at the cotangent of cosecant. Cosecant is the triangle with a hypotenuse x and then a opposite side of 1. Or with those as its ratios, but that doesn't matter. And then that means that our adjacent side must be x squared minus 1. So our d over dx of cosecant inverse of x is equal to negative 1 over the absolute value of x times by the square root of x squared minus 1. That, my friends, is the answer. Now I have 2 final problems for us to solve together, and then you'll be free to go. Very simple for this first one. Very incredibly simple. So, whenever I said the derivative, I obviously meant with respect to x, even though that's a function of t. Mwaha! No, I'm kidding. I won't do that to you. D over dt. So taking this derivative with respect to t, well, this is just simple. This is just a review. Our prime of t, then, must be equal to 1 over the square root of 1 minus t squared. And that's our answer. For this next one, we take the derivative of the outside function first. So we take the derivative of the natural logarithm with respect to arcsecant of t. So we get 1 over arcsecant of t times by the derivative of secant, which is 1 over the absolute value of x, or in this case, t. Times by the square root of t squared minus 1. And that's it. That's its derivative. Well, that's all I have for you today. I hope you found this video informative, and if you did, please hit the like button. If you'd love to see the proofs of things in math, then please subscribe to my channel. I hope you all have a wonderful rest of your day and enjoyed. Bye-bye.